Good evening. So, the topic for today's class is applications of Gauss theorem or the Gauss's law. Gauss theorem we discussed in the last class. Let's have a quick revision of that. In the last class, we discussed about the concept of electric flux and this Gauss theorem. What is Gauss theorem says? Gauss theorem says that the net electric flux, suppose this phi E is the flux passing through a closed surface, is 1 upon epsilon 0 times the net charge present inside that surface. What we require here is the closed surface, and we call that closed surface as the Gaussian surface. This charge should be enclosed inside that closed surface, inside that Gaussian surface. Okay, and from definition of this flux phi E, which is the measure of the number of field lines passing through a surface when that surface is kept normal to the electric field. So according to that, this phi E is equal to E dot A. If I take the total flux phi E, so this E dot A, which is equal to this E into A into cos theta. The theta is the angle between the electric field intensity and the area vector. So if theta is equal to 0, we will be having the maximum flux. And when theta is equal to 90 degree, we will be having the zero flux. No flux would be coming out from that surface if theta is equal to 90 degree. So this was the Gauss theorem, which states that the net electric flux through any closed surface is 1 upon epsilon 0 times the net charge present inside that Gaussian surface. Okay. So now, as far as the applications of this Gauss theorem is concerned, the most important thing would be the choice of the Gaussian surface, because your charge should be enclosed inside the Gaussian surface. So choosing a Gaussian surface is of prime importance if you want to apply the Gauss theorem. Okay, so we will see how to select the Gaussian surface for a given problem. So what application means? Application means the use of the Gauss theorem. Okay, so use is you will be given a charge distribution. Okay, and because of the charge distribution, you have to find the value of the electric field intensity at a given point. For example, we will be seeing the three applications, the three uses of the Gauss theorem. Okay, so number one, for example, if I have a very long wire, and on that long wire, if I consider the charge which is distributed, so your charge is distributed along the length of the wire. Okay, so we call that as a linear charge distribution, and the density which is representing here is called as a linear charge density. Okay, so the linear charge density is the charge per unit length. If your charge is spread on a given surface, then that is called as the surface charge density, the charge per unit area. If the charge is distributed over the whole volume of the conductor, then that is called as the volume charge density, the charge per unit volume. So these three type of densities will be having different units also. For example, the linear charge density will be having the unit coulomb per meter, charge per unit length. Your surface charge density would be having the unit charge per area, therefore it is coulomb per meter square. If the charge is distributed over the whole volume, it would be coulomb per meter cube, because it includes volume. Okay, so for this applications part, okay, what is of importance is the choice of the Gaussian surface for finding the electric field intensity at a point because of the given charge distribution. So we will be discussing in this very class three type of charge distributions. Okay, let us now see those one by one. They're simple. Okay, but what you use here is the Gauss's theorem. So your choice of the Gaussian surface should be such that this theta, if this theta is equal to 0 degree, maximum flux would be coming out because cos 0 is equal to 1. Okay, if this theta is equal to 90 degree, no flux at all would be coming out because the cos 90 is 0. Okay, so we will be choosing the Gaussian surface such that your theta would be either 0 degree or 90 degree. Okay, so these three, so in these three applications we will be choosing the Gaussian surface because that is in our hand. So looking to the symmetry of the problem, your choice of the Gaussian surface should be accordingly. Okay, let us now proceed with the applications of the Gauss theorem. So those three applications that we will be discussing, you may please see here. Number one, the first application is the electric field at a point due to an infinite linear charge distribution. That is when the charge is spread over the length of the conductor. That is called as a linear charge distribution. So you have to find the electric field at a point at certain distance due to this infinitely large linear charge distribution. The second application that we will be dealing with today is the electric field at a point due to an infinitely large plane sheet of charge. Now, a plane sheet is a two-dimensional surface. So the charge will be spread over the area of that. So what we will be dealing here is the surface charge density, charge per unit area, coulomb per meter square. Number three, you have to see the electric field at a point due to a thin spherical shell, thin spherical conducting shell. So a shell means a hollow sphere. So your sphere would be hollow, it is conducting. Okay. So whenever we give charge to a certain hollow conductor, the charge spreads uniformly over the whole area. Okay, so here also we will be dealing with what is called as the surface charge density because your conductor is a shell, it is hollow, therefore the charge is spread over the whole area, right? So we will be dealing with these three applications one by one. The important thing that you keep in mind is the choice of the Gaussian surface. You will choose your Gaussian surface such that no much mathematics is required. Okay, so let us now see. So let us now start with the first application, the electric field at a point due to an infinite linear charge distribution, and you will see these two remain. Okay. So for this, I would consider a straight wire. The straight wire is a linear one. Okay. So if I consider a straight wire which is infinitely long. Suppose this is the part of that wire, it is going in this direction as well as in this direction because it is infinitely long. There is no definite length. Okay, so what I am taking here is the linear charge density, that is the charge per unit length of this wire. This is my wire, which is infinitely long. So for this wire, the charge per unit length, linear charge density it is called, I represent it as, suppose, lambda. This is a symbol for that. The linear charge density is represented by lambda. Okay. So if I consider my observation point where I have to find the electric field, because my application is to find the electric field at a point due to this linear charge distribution. So suppose if I give a positive charge over here, so that positive charge is uniformly distributed over the whole length of this infinitely long wire, something like this. It is uniform density. Okay, so suppose if I consider my point P, my observation point P somewhere here at a distance r from the y. This r is the perpendicular distance of this observation point P, okay, from this wire. So my first application is to find the electric field intensity at this point P because of this infinitely long wire. Okay. Let's now see how to proceed where this lambda is the linear charge density. So we have to use here what is called as the Gauss theorem. And Gauss theorem says that the net electric flux through any closed surface is 1 upon epsilon 0 times the total charge or net charge present inside the surface. Okay. So right now if you see these charges, they are open. They are not enclosed inside the conductor. Okay, because their charges are present on the surface of the conductor. They are not enclosed. So in order to apply the Gauss's theorem, we have to enclose these charges. Enclose these charges means we have to choose a closed surface, an imaginary closed surface. Okay, that surface may be imaginary, and we call that imaginary closed surface as the Gaussian surface. Okay, so how to choose the Gaussian surface in this very case, because it is infinitely long. Okay, so for doing that, what will I do? I will choose a section of this infinitely long straight conductor, right? So if I do that, suppose if I take this very section of the y, okay. So if I take, suppose if I take this point as A and this point as B, okay, then this AB is the section of that infinitely long wire. So if I give the length of this section as L, suppose if this L is the length of this section of the infinitely long wire. So I cannot enclose the infinitely long wire, but yes, I can very well enclose this section AB of the wire. Okay, so how to enclose it now? Okay, keep in mind what is important is the symmetry of the charge distribution. Okay, for example, if I draw a straight line from here, a straight line which is parallel to the linear charge distribution, something like this. Similarly, suppose on the other side of this wire, that is on the left hand side, okay, suppose if I consider another point which is at the same distance at this point, so as this point P from this wire, if I give this name, suppose P dash, so the value of, so the distance of this P dash from this wire is also equal to R. And again from this point P dash, if I draw a line which is parallel to the infinitely long distribution, then is something like this. This is the point P dash, this is the point P. Okay, so both the points P and P dash, they are at the same distance R from the wire. Okay, now what will I do? Suppose if I draw a cylinder, something like this. This is a cylinder. This is suppose a cylinder. So this cylinder now has enclosed not the whole wire but the section AB of my infinitely long conductor. The length of this section AB is equal to L. Therefore, the length of the cylinder will also be equal to L. Okay. But by drawing this imaginary cylinder, what have I done? I have enclosed these many charges. Okay. I have enclosed these many charges here. Okay. So this imaginary cylinder would be my Gaussian surface. This is my Gaussian surface. Okay, this is my Gaussian surface. So if I do that, now I can take one point here also, I can take one point behind this board also, and all those points would be at a distance R from the wire. So what this is representing is the curved surface of the cylinder, this one. This is representing the curved surface, and these two top and bottom surfaces, they are the flat surface of the cylinder. Okay, suppose if we consider this as the cylinder, then this is the curved surface and these two are the flat surfaces. Okay, now suppose if this AB is equal to L is the length of the cylinder, and the radius of the cylinder would be equal to what? The r. Okay, so r will become equal to what? R would be the radius of the Gaussian surface, which is my cylinder in this case, which is my cylinder. Okay, so at this point P, if I consider a very small area element here, yesterday we discussed about the area element, a very small section of the area of a large surface, we call it as the area element, right? So here, suppose if I consider a very small area of this cylinder, something like this, okay, here, because it is curved like this. So I consider a very small section of that, and this is my dA. This dA would be what? The area element. This dA would be equal to what? The area element, right? If I draw area vector, the area vector is always drawn outward normal to the surface, right? Outward normal to the surface. So if I draw the outward normal here, it would be something like this. This is my dA vector. So my dA vector would be along this direction. Okay, my dA vector would be along this direction. If I consider the electric field at this point because of the charge over here, okay, that would also be what? Radially outward, because every charge will be producing its electric field, okay, at these respective areas. So for this area, if I consider my electric field would also be in the same direction as that of the area vector. So for this whole curved surface, the angle between the area vector and the electric field would be equal to 0 degree. It is equal to 0 degree because the electric field and the area vector, they are in the same direction. Okay, for this entire curved surface. Now look at these flat surfaces, the top surface and the bottom surfaces. Okay, here if you see, here if I consider a small area element here, okay, my electric field would be in this direction, radially outward direction here, but my area vector, which is outward drawn normal, okay, so my area vector, suppose dA if I take here, my area vector dA would be here because this is my flat surface, so the area vector would be along the outward normal in the upward direction. So for this flat surfaces, the angle between electric field intensity and the area vector would be equal to what? 90 degree. So here theta is equal to 90 degree. With the same token, if I take the area element here, again the electric field would be in this direction and the area vector would be here, because now the outward drawn normal would be in the downward direction. Outward drawn normal would be in the downward direction. So in this case also, your theta is equal to 90 degree. What does this theta is equal to 0 degree and theta is equal to 90 degree signify? Okay, it signifies that when theta is equal to 0 degree, the flux is maximum. When theta is 90 degree, the flux is minimum, because from the definition of flux, phi is equal to E into dA into cos theta. Okay, so when theta is equal to 0 degree, phi is maximum, theta is 90 degree, the flux is 0. Okay, so what we have here is theta is equal to 0 degree for the curved surface. That means that whatever the flux that would be coming out from my Gaussian surface, whatever the flux that is coming out from this Gaussian surface is from the curved part of the cylinder, and no flux, no field line is passing through these two plane surfaces. Why? Because theta is equal to 90 degree. So all the flux would be coming out from where? From the curved part of the Gaussian surface. Okay, and therefore the flux coming out from the area element of the curved surface would be equal to, this suppose d phi is that flux, so d phi would be equal to E multiplied by dA, because theta is equal to 0, so cos 0 would be equal to 1, so it would be equal to E into dA. Okay, so therefore the total flux from the Gaussian surface, total flux. I know the flux from this small area element. I want to calculate total flux from that whole Gaussian surface, which is only the curved part of the cylinder. Okay, so that would be obtained by integrating my small flux. Okay, therefore here if I see my suppose the total flux is phi, and that would be equal to integral of what? This d phi. Okay, so if I put the values here, so it would be equal to integral of E multiplied by dA. E multiplied by dA. So electric field, it is constant everywhere on the curved surface. Why? Because all the points here, like suppose this P and P dash, the point over here, the point behind this board, they are at the same distance from my linear charge distribution. Therefore electric field will be constant at every point on the curved surface of the Gaussian surface. Okay, so therefore my flux phi would be equal to, this E will come out of the integral sign, right? This E would come out of the integral sign. So my flux phi would be equal to E multiplied by integral of dA. Okay. Now what this integral of dA would be? Integral of dA would be giving me the whole curved surface area of my cylinder. The whole curved surface. Why only curved surface? Because the flux is coming out only from the curved surface. There is no flux coming out from the from the flat surfaces. Okay, and therefore what we need to take into account is only is the curved surface area of the cylinder. And we know that the curved surface area of the cylinder is given by 2 pi RL. So it would be equal to E into 2 pi R multiplied by L. What is R here? R is the radius of the cylinder. It is also the distance of the observation point from the linear charge distribution. What is L? L is the length of the section of my infinitely long wire. Right? So this is equation number 1. Let us suppose equation number 1. So phi is equal to E into 2 pi into RL. So far we haven't touched this Gauss theorem. Okay, now we will come to the Gauss theorem, because we have obtained now what? The flux coming from that closed surface. So now according to my Gauss theorem, now we will apply Gauss theorem, because our topic is the applications of Gauss theorem. Okay. So now if you see, if you apply my Gauss theorem now, so applying Gauss theorem. Okay, now what Gauss theorem says? Phi, the net electric flux through any closed surface, is 1 upon 1 upon epsilon 0 times the net charge present inside that surface. Now the question arises, what is the net charge present over here? Okay, I have given you lambda is the linear charge density, the charge per unit length, right? The charge per unit length is lambda. What is the length of the section? L. Okay. So the charge enclosed inside this Gaussian surface is equal to the charge on this length element. Sorry, this section of the whole wire. That would be equal to what? Lambda multiplied by L. Because this lambda would be measured in coulomb per meter. And in SI unit, if you measure L in meter, so coulomb by meter into meter would be giving me coulomb, the total charge. Okay, so what we have here is, so phi is equal to 1 by epsilon 0 multiplied by Q net would be equal to what? Q net would be equal to lambda multiplied by L. Lambda into L would be the charge on this section of the infinitely long wire. right? So it would be equal to lambda multiplied by L. This lambda into L is the net charge present. Let this be equation number 2. If you look at the equations 1 and 2, their left hand sides are equal. This is the flux, this is also the flux, so we can very well equate the right hand side. So if I equate the right hand sides of equations 1 and 2, what I have is this E multiplied by 2 pi RL equals 1 by epsilon 0 multiplied by lambda L. Okay, so my L would be cancelled by this L. What I'm left with is the expression for the electric field intensity, and that would be equal to lambda divided by 2 pi R epsilon 0. This is the beautiful expression for the electric field intensity at a point because of infinitely large linear charge distribution. If you look at here, lambda is constant, the linear charge density is constant, 2 pi is constant, epsilon 0 is constant. So this E is proportional to 1 over R, that is this E varies inversely as the distance. For a point charge, we have seen E varies like 1 by R square. For a infinitely large linear charge, E is varying like 1 by R. This should be keep in mind. Okay, so this E is proportional to 1 by R. Please keep this thing in mind. Okay, so this was for the first application, the electric field at a point due to an infinitely linear charge distribution. So E is proportional to 1 by R. This is the concluding result. The whole formula is this, lambda upon 2 pi R epsilon 0. Okay, the value of epsilon 0 you can very well find in your book. Lambda would be given to you if numerical problem comes based on this, and you are asked to find the value of the electric field at a given point. Okay, now come to the second application, okay, which is the electric field at a point due to infinitely large plane sheet of charge. Let us now look at it. That would be the case of surface charge density. Unlike here the charge was distributed over the length L, over the infinite length of the wire, but there what you have is not the linear charge but the surface charge density. Okay, so now my second application for this Gauss theorem is electric field at a point due to an infinite plane sheet of charge. Sheet means a two-dimensional surface. And of course, it will be uniform. Okay. As far as our discussion is concerned, we will be dealing only with the uniform distribution of charges. Okay. So, if I have an infinitely large plane sheet of charge, we assume this board in front of you. Okay. It of infinitely large area, and if you give certain amount of charge to it, that charge will be distributed uniformly over the whole surface. Okay. Then if I am standing here, I have to find the electric field intensity at this point because of that infinitely charged distribution. If I move myself away from the board, I have to find electric field intensity here. So in the first case, we saw that the electric field intensity was varying like 1 by R. Okay, let us see the result for this. Okay, so if I consider an infinitely large plane sheet of charge, something like this. It is infinitely large plane sheet of charge. So here charge is distributed uniformly over that entire surface, something like this. Okay, so So this is how the charge is distributed. Okay, and if I assume that surface charge density, that is the charge per unit area, the surface charge density we call it as, the surface charge density is suppose sigma. Sigma is the surface charge density. Okay, charge per unit area, coulomb per meter square. Its unit would be coulomb per meter square. C is coulomb, M is meter. So coulomb per meter square. Now I want to find the electric field intensity at a point. Suppose that point is P. That point P is somewhere here. You can assume it like this. Your plane sheet of charge is something like this. Okay, perpendicular to this board, the huge plane sheet of charge, and this point P is just opposite to that. Okay, here somewhere, which is at a distance, suppose certain distance R again from this infinitely large plane sheet of charge. So you have to find the electric field intensity now at this very point. Again, these charges are open. It is a two-dimensional surface. In order to apply Gauss theorem, what we require is the charges should be enclosed. So we have to enclose the charges, right? That is what we have to keep in mind. So how to do that? Again, we have to choose an imaginary surface, which we call it as the Gaussian surface. Okay. Now for doing that, if I consider another point, okay, which is right behind your infinitely plane sheet of charge. Suppose if this is your plane sheet of charge, this point P is in front of it at a distance R, suppose, and if I consider another point P dash here, which is behind that infinitely large plane sheet of charge at the same distance. Okay, so if I consider that point P dash somewhere here, okay, this point P dash is somewhere here. So point P is in front of the infinitely plane sheet of charge. P dash is behind that. Okay, and if I assume this distance as R, suppose this distance is R. This distance is also equal to R. Okay, because this point P dash is the same distance. Okay. Now to enclose these charges, that is, I have to consider an imaginary surface, my Gaussian surface. Okay. So again, if I take a circle here, if I take a circle here, such that the line joining the point P and P dash is passing through the center of this circle. Okay, I have considered a circle here on this plane sheet of charge, such that the line which is joining P and P dash is passing through the center of the circle. Okay, then if I construct a circle of the same area, keeping this point P dash as the center and this point P as the center, and if I join them, if I join it like this, I have joined it like this. Okay. What you can see here, I have inserted a cylinder. I insert a cylinder such that these many charges are enclosed inside that cylinder. So this cylinder now, which is my imaginary surface, which is enclosing the charges on this plane sheet of charge. Okay. This cylinder would become what? My Gaussian surface. My Gaussian surface. Okay. My Gaussian surface. If I assume these circles 1, 2 and 3 of suppose area A. So A is the area. Which area? It is the plane area. Okay, again if I consider this as my cylinder, then this would be the curved part. Okay, and these two are the plane surfaces of that cylinder. Okay, right? So this area, which is the plane area of the cylinder, not the curved surface area. There is a plane area of the cylinder, which is my Gaussian surface. Okay. Now, if you look, how the area vector will look like? Here, the area vector would be outward drawn normal. So my A vector would be somewhere here, outward drawn normal. Here, my A vector would be somewhere here, outward drawn normal. What about the curved surface? What about the curved surface? My area vector, if I consider a small area here somewhere, my area vector would be in this direction. Okay, suppose if this A dash vector, this A dash vector would be in this direction. If I consider the area here, my A dash vector would be in this direction. If I consider my A dash here, that would be in this direction. Okay, so this A is representing the plane area of the cylinder. Okay, so if you look at the electric field now, these charges are distributed like this. So the electric field intensity would be along this direction. There is no electric field line coming in this direction. That is, there is no field line coming through the curved surface. Okay, the electric field will always be radially away here somewhere, right? So my electric field would be in this direction. Here my electric field would be in this direction. Okay, so electric field would be in this direction. Here, if I consider the area here somewhere, this is my A dash vector and the electric field is here somewhere. So here my theta is equal to 90 degree. Here my theta is equal to what? 0 degree. Here as well my theta is equal to 0 degree. So for these two plane surfaces, theta is equal to 0 degree, and for all the curved surfaces, if I consider the area element, the value of the angle is 90 degree, and therefore there is no flux coming out from the curved surface. All the flux would be coming out from where? From the plane surface area of the cylinder. Okay, so if I calculate the total flux coming out from the Gaussian surface, okay, so what is that? So the flux coming out from the Gaussian surface, the flux coming out from the Gaussian surface, again from definition, the total flux is phi E. E means electric field, phi E, the flux, electric flux. Phi E is electric flux, which is E into A into cos theta. For this, cos 0 is 1, therefore this would be equal to simply E multiplied by A. There is no cos factor. Why? Because cos 0 is 1. There is no flux coming out from the curved surface because theta is 90 degree. So cos 90 is 0. So the total flux coming out here is phi E is equal to E into A. But there are two surfaces. Okay. One surface is here, another surface is here. Okay. So the total flux that is coming out from this whole surface, okay, from this whole surface would be in this direction as well as in this direction. Therefore, we should multiply it by 2. It would be equal to 2 into E into A, right? So this phi E is equal to 2 into E into A. Why I have multiplied by 2? Because there are two directions in which the flux would be coming from this very area, in this direction as well as in this direction, and both of these flux would be added up. Why added up? Because both of them are coming outside the surface. Okay, so therefore EA plus EA would be giving me what? 2 times E into A. Okay, that is the question number 1. Now bring into picture what is called as the Gauss theorem. Okay, because we will see the application of that. Okay, we haven't found the value of E, that was our objective. Okay, so again by applying Gauss theorem, what I have here is phi E is equal to 1 upon epsilon 0 times the net charge present inside it. Okay, so this 1 upon epsilon 0 multiplied by the net charge present inside. Now, what is the net charge present? What is sigma? Sigma is charge per unit area. The charge per unit area multiplied by the area would be giving me the charge enclosed inside that. Okay. So what is the value of this Q net? Is sigma multiplied by A. Okay. So sigma into A, that is the charge per unit area multiplied by the area, would be giving me the net charge. Okay. So that is the equation number 2. So the left hand sides of equations 1 and 2 are again the same, so we can equate the right hand sides. So therefore from 1 and 2, if I write this 2 into E into A is equal to 1 upon epsilon 0 multiplied by sigma into A. So this A would be cancelled by this A. What I'm left with is E is equal to sigma divided by 2 epsilon 0. This is another beautiful result. And this should be a non-intuitive result for you. Why non-intuitive? Because if you see, what was our objective is to find the electric field at a point due to an infinitely plane sheet of charge. So we started taking this as our infinite plane sheet of charge. We considered a point P at a distance r from the plane sheet of charge. If you look at the final expression for the electric field intensity, nowhere this r is coming into picture. Okay, that means that irrespective of the distance of the observation point from the infinite plane sheet of charge, electric field should remain constant. Okay, how is that possible? This is the first case that we are seeing. For a point charge, we observe that the electric field is varying like 1 by r square. For just in the first application of this, we saw that electric field is varying like 1 by r. But here, the electric field is independent of r. Okay, how is that possible? It is possible because, again, if I consider this as my infinitely plane sheet of charge, I am standing here. Only few charges are in my field of view. Okay, therefore the value of charge would be small. Okay, if I move myself away from that plane sheet of charge, more charges will come into my field of view, right? So the value of charge would be increasing. Okay, so the increase in the distance is getting offset by increase in the value of charge. Okay, and this is the reason why the electric field intensity is independent of the distance. This E is equal to sigma divided by 2 into epsilon 0, right? So this E is equal to sigma by 2 epsilon 0 is the electric field expression at a point due to infinitely large plane sheet of charge. Okay, we will explore it more in detail in our coming classes. Okay, we will start with this expression. Okay, if I take negative charges distributed, I would get the same result. Only the sign of the sigma would get changed. Sigma would be negative, right? Because then your theta will not be 0. Why? Because your electric field would be in this direction, A would be in this direction. The angle would be 180 degree. Cos 180 is -1. Therefore, there would be a simple minus sign over here if you take the negative charges distributed here. Otherwise, the expression would remain same in magnitude. On direction would get changed, right? This was second application. Let's now see the third and the last application for this Gauss theorem as far as our examinations are concerned. So the third application is to find the electric field at a point due to a thin spherical shell. Okay, as I discussed in the introduction, a thin shell is a hollow sphere. Okay, and whenever you give charge to a hollow sphere, that charge is distributed uniformly over the whole area of that sphere. Okay, so let's now see that the third application. The third application is electric field at a point due to a thin spherical shell. Okay. A thin spherical shell. Okay. So I will consider a spherical shell. This is the spherical shell, suppose. A hollow sphere, not a circle but a sphere. This is a sphere. Suppose this, I'm sorry, O is the center of the spherical shell, and this R is the radius of that spherical shell. This is my spherical shell. Okay. Then I have to find the electric field at a point due to the spherical shell. Now this point, it may be outside the spherical shell, it may be on the surface of the spherical shell, or it may be inside the spherical shell. So you have to find three expressions here, right? Three expressions for three different positions. Okay, and you will see how the electric field varies like that. So let us now take the first case. Case 1. When the point is outside the spherical shell. The point is outside the spherical shell. That is, my point is somewhere here, right? The point P is somewhere here. Okay, and the distance of this observation point P from the center of the sphere is R. Okay, now suppose if I give an amount of charge, let us say plus Q here, okay, to the spherical shell, then that charge would be distributed uniformly over the whole surface of the spherical shell. There would be no charge present inside the spherical shell because there is hollow space there. There is nothing, no medium is present there inside except the vacuum. It is hollow. Okay, so nothing is inside, therefore all the charges would be distributed uniformly over the whole surface of the spherical shell, right? So in my first case, my point P is outside the spherical shell. Okay, so at this point I want to find the value of the electric field. Okay, how to do? I have to apply Gauss theorem. Are these charges enclosed right now? No, they are not enclosed. Okay, Gauss theorem is applicable only for the enclosed charges which are enclosed in a conductor, enclosed in a shell. So I will be enclosing these charges in an imaginary surface. Okay, and that imaginary enclosed surface is called as the Gaussian surface. So I will be taking again a sphere, a spherical Gaussian surface I will be considering, right? This is my Gaussian surface I am drawing. The radius of this Gaussian surface would be equal to this distance R from the observation point from the center of the spherical shell. Okay, so this distance is R. So R is what? R is the radius of my Gaussian surface. Something like this. Okay, so very good. What is the flux here? If I consider this is my area element dA, this dA would be the area element, and the area vector would be outward drawn normal. So this dA vector would be here. The electric field intensity will also be radially outward. So my E would also be along the same direction, and therefore I have chosen a sphere deliberately. Okay, because that would always be giving me what? Theta is equal to 0 degree. Otherwise the choice, this is the Gaussian surface, the choice of the Gaussian surface is in your hand, but you have to choose the Gaussian surface such that it simplifies your mathematical effort. So by choosing this spherical Gaussian surface, I have at all the points theta is equal to 0 degree. At any point I take, theta will always be equal to what? 0 degree. And therefore my flux coming out from the area element dA will be equal to what? Phi E is equal to E multiplied by dA. Again, there is no cos factor coming over there because cos 0 is equal to 1. Okay, so phi E is equal to E into dA, and therefore the flux coming out from the whole Gaussian surface phi E would be obtained by integrating this. That's an integration of phi E. Okay, that would be equal to what? Again, E would be constant at all the points, so E into integration of dA. What this dA would be? Integration of dA would be the whole surface area of my Gaussian surface. The radius of that is R. Okay, so this phi E would be equal to E multiplied by 4 pi R square. Integration of dA would be the whole surface area of my spherical Gaussian surface. So phi E is equal to E into 4 pi R square. That is equation number 1. Number 1. Okay. Again, I have to apply Gauss theorem for this first case. So for this first case, if I apply my Gauss theorem, so applying Gauss theorem, my flux, the total flux coming out, phi E, this is capital Phi. Okay. So phi E is equal to 1 upon epsilon 0 times the net charge present inside the Gaussian surface. Well, this is my Gaussian surface. What is the net charge present inside? Is this Q. Okay, because this Q was the charge given to my spherical shell. This is the spherical shell. Okay, so this phi E. This phi E is equal to 1 upon epsilon 0 multiplied by Q. That is equation number 2. Okay. Again, equating the left hand sides of equations 1 and 2. What I have is E multiplied by 4 pi R square is equal to 1 upon epsilon 0 multiplied by Q. Okay. I am reaching at a result that I have seen earlier as well. Okay. If I bring it here, it would be 1 by 4 pi R square. I have brought it in a denominator. So E is equal to 1 by 4 pi R square into 1 upon epsilon 0 into Q. If I rearrange it, okay, please look at this expression very clearly, very carefully. So E would be equal to, if I rearrange it, if I change the positions, it would be 1 by 4 pi epsilon 0 Q divided by R square. We have seen this expression when we discussed the electric field intensity at a point due to a point charge. It is not a point charge, but the expression is coming out to be the same. So whenever we find the electric field intensity at a point due to a thin spherical shell, when that point is outside the spherical shell, the electric field is such that the whole charge is present right at the center of the spherical shell. Because this R is what? R is the distance of the observation point from the center of the spherical shell. So here it is not a point charge distribution, but the charge is distributed on the spherical shell Okay, but the expression is such that the charge is placed, the whole charge is placed at the center of the spherical shell. So in the first case, your electric field is varying like 1 by r square. E is proportional to 1 by r square because Q